Welcome to our presentation of continuous KU band signal acquisition. This project was a collaborative effort between students and a teacher at the second high school of Relesia. We set out to build a radio monitoring station using affordable everyday satellite equipment and a modern cloud computing.
The KU band, which spans frequencies from 12 to 18 GHz, is essential for satellite TV, weather monitoring, and radar. Even the sun emits in this band. Professional equipment for this band is usually very expensive. Our aim was to use cheap and available hardware to make data collection accessible for our tight budget. We learned a lot of things in the process, as you will see in the following.
Our first setup was very simple. We used an 80 cm parabolic antenna and a low noise block connected to a handheld signal meter. By using a 12 voltage battery, we were able to move the equipment and observe how signal intensity peaked when pointing at the sun or catching reflections from nearby buildings. This is nice, but it would be better to be able to record the signals as we cannot watch the signal meter all day.
We hacked the signal meter a little and we connected its output to an Arduino microcontroller. However, we quickly found out that the Arduino's built-in converter was too coarse, providing only 82 distinct digital values for our 0.4 volt signal range. It is like trying to take a high definition photo with a Minecraft camera. In order to see small details, we have to find a way to represent the signal with more precision.
To improve our precision, we added an external 16-bit analog to digital channel, the ADS 1115. This allowed us to zoom in our signal. Now, instead of 82 steps, we can represent our signal with 2 to the 16th power steps, which is about 65,000 steps. This high resolution is critical because our signal has a lot of fluctuations. We also used an SD card module in order to record data in a text file. This allows us to use a PC to process the data.
In this photo, you can see our setup. In the lower right, you can see the signal meter. The two red wires carry the signal from the signal meter to the breadboard and the analog to digital converter, which is shown in the upper right. The data is then fed up to the Arduino, which is shown at the lower left. The SD card in the upper left is used by the Arduino to store the data.
In our 24-hour dataset, we noticed a consistent pattern. The signal rises at sunshine, peaks at midday, and cools off after sunset. We believe this is thermal drifting, where solar heating affects the electronics in the LNB, causing the recorded voltage to shift. We also observed peaks that are due to interference with cell phones, as well as sharp isolated peaks that may be due to aircraft or satellites.
Next, we added a Raspberry Pi to act as our internet gateway. We have connected it to the Arduino using a USB cable. It reads data from the Arduino and uses a simple Python script to upload it to the Adafruit IO cloud platform. So our station operates autonomously on the school terrace and can be monitored remotely. We retained the SD card module so as not to lose data during network out.
So now we have live data from the school roof. Our Adafruit IO dashboard gives us real-time view of the signal. It features live gates, a raw data stream, and historical graphs that show us the signal trends from the last hour up to the previous 7 days. The data can be downloaded to our PC and then processed there.
At this point, it is worth to see some representative graphs. The signal depends on many factors such as the sun's position, temperature, precipitation, humidity, cloud coverage, and passing cloud edges. More notably, rain creates a very high terminating peaks in our data because water on the dish and in the air scatters and emits radio waves.
In conclusion, we successfully built a low-cost monitoring system capable of resolving both long-term and short-term variations. In the process, we learned a lot of things. First, precision is important, as the variations are subtle and in many scales. The use of the external ADC was very important. Second, the sky speaks. This means that rain, clouds, humidity, and temperature all influence our data. And third, we have learned how valuable is cloud integration. In the process, we have learned a lot about coding as well as the physics involved.
In the future, we plan to use two antennas in order to distinguish signal from noise. We also plan to add a weather station to investigate data correlation with meteorological data. Finally, as the next step in our investigation, we plan to use software-defined radio to perform spectral analysis of the signal.
Thank you for your attention.